Hello there, Mr. Sutton here, bringing you this lesson on rectangular approximation method, or RAM, part 1. In this one, we're going to be determining area under a curve using rectangles.
Let's open things up with a real-life application. Let's say a truck driver sets her cruise control for 60 miles per hour, as shown in the graph here. We're graphing velocity versus time. We want to know her distance traveled in the first 3 hours using geometry. We could definitely do this pretty quickly without geometry. Pause the video and see if you can figure out how to do it with geometry on this graph. All right, let's see what we came up with. So without geometry, we would just multiply the 3 hours times the 60 miles an hour. Every hour she goes 60, so 3 of them gives us 180 miles traveled. Now, how can we represent that geometrically? Well, every single hour on here, you have an area of 60 under this velocity curve. So if you want to know the distance traveled over 3 hours, that would be the area from 0 to 3 under the velocity curve. And if you take a look at the area here, we've got base times height. Our base is 3. The height is going to be 60. That's the velocity. And there you have it, 180 miles done with geometry. So the next question then, since now we figured out that area under the curve represents distance traveled if you're graphing velocity, what if we have a space shuttle taking off with the velocity shown in this graph here? How could we find the distance traveled by the space shuttle in the first 3 hours? So if you're trying to do this the way we did it up here, it's definitely not going to be an exact match. Pause the video and see if you can figure out how you could do it, though. All right, what'd you come up with? Well, there's no good shape for this, so really what we're going to tackle that with today is by using more rectangles. One rectangle, clearly not enough, but what if you had 3 rectangles, or 4, or 5, or maybe an infinite number of rectangles? More on that later. It's time to talk about RAM. Not random access memory, this is the rectangular approximation method, also known as RAM or taking a Riemann sum. So these all mean the same thing, which is estimating the area under a curve by finding and adding the area of rectangles. Why rectangles? Well, can you think of an easier shape to find the area of? It doesn't get much easier unless you had squares. So there's 3 ways that we can actually draw these rectangles. There's more than 3, but these are the big 3. One of them is called LRAM. This is when you use the left corner of the rectangles to touch the curve. So here's a sample curve. This is part of the graph of x squared. So if we want to draw a rectangle so the left corner is touching, we're not even going to see the first rectangle because the left corner would be touching the origin here. The second rectangle would come up to here, though, and then our third rectangle would come up here, and I believe this is the y value 4. So that's one way of doing it. Now, some people might be unsatisfied with this because we're leaving out all this white space under the curve. So there's another method, RRAM, where we use the right corner of the rectangles to touch. And by the way, LRAM is not always going to fall short. It all depends on which way your curve is going. There are other curves where LRAM would give us too much. But let's look at RRAM for this one curve now. So this is where your right corner of your rectangle is coming up to the curve. So right there, and another rectangle coming all the way up so the right corner touches up there at positive 9. Now this one is giving us too much area. These are all approximations, so none of them are going to be exact. But this is definitely overdoing it. So there's one more way to draw these rectangles. MRAM. This is by using the midpoint of the top of the rectangle. So here's our first rectangle. Here's our second one coming up to about there. And our third rectangle will come up to about here. Now this one, over-approximates in some places and under-approximates in others. And kind of the hope, I guess, is that the over and the under kind of cancel each other out. Now, do they exactly cancel each other out? They do not. But you're at least coming a little bit closer than these other 2 methods for most of the curves you're going to see. However, we are going to use all 3 of these. For our first real example problem, we are going to use LRAM to approximate the area under x squared from 0 to 3 with 3 subintervals. And they have to tell you how many subintervals, otherwise you could use as many rectangles as you wanted. So using only 3 rectangles. Now for LRAM and RRAM, it's a good idea to start by putting the endpoints of each subinterval in a table as x values and then finding the corresponding y values. So for our x values, our endpoints of the rectangle, we have one rectangle going from 0 to 1, and then another from 1 to 2, and then the last one from 2 to 3. And by the way, we're basically just figuring out the area under this curve right here using these rectangles. So we'll refer back to this picture a few times as we do this. Now the y values, those are just going to be when you plug 0, 1, 2, and 3 into x squared here. So 0, 1, 4, that's 2 squared, and 3 squared is 9. In terms of your actual rectangles that we're going to add together, the size of the subinterval, the change in x that is the base of each rectangle. And you see here they each have a base of 1, 0 to 1, 1 to 2, 2 to 3. Again, we are just looking at these rectangles in this picture over here. So going back to our math now, for LRAM, we're using the left endpoint's y value for the rectangle's height. So those are going to be the heights 0, 1, and 4. Again, looking at that picture, we have a height of 0 for this first rectangle, 1 for the second, and 4 for the third one. So let's write some fancy notation here. The way we say the area under the curve from 0 to 3 is by using this integral notation. This is a definite integral. We've seen this when we did it geometrically before. And that's going to be those areas added together. So we have 3 base times height terms. We have 1 times 0. This is the base of the first rectangle times its height of 0, plus 1 times 1, plus 1 times 4, the base of the last rectangle times its height. Adding all those together, we've basically got 0 plus 1 plus 4, which is 5. That approximates the area under that curve. Is it a good approximation? Maybe not, but it is an approximation. It doesn't have to be exact. That's the whole point of an approximation. One other thing I'll point out before we move on to another one of these is that on the AP free response exam, part of the exam, you do not actually need to simplify this out. You don't have to write 5 at the end. You actually could just leave this in this form right here, where you just write out the sequence. Having said that, you do sometimes need to approximate these on the multiple choice section, and then you actually will need to find the final answer.
And one last thing before I move on. This equals that I wrote here actually should not be an equals because we are approximating the area under this curve with rectangles. We're not actually giving the true area. Since this is not the true area, truth in advertising forces us to not write equals, but instead to write approximately equals. Like so. So if you do not write approximately equals on one of these integrals where you're trying to approximate an area, you will lose a point on an AP exam. So make sure you have truth in advertising. If it's an approximation, spell it out with your equals notation here. Now that we've got one RAM example under our belt, let's try another one. This one, we're going to find the area under the same function, x squared, this time on the interval from 2 to 10 using RRAM with 4 subintervals. Pause the video and see if you can figure out what you need to do on this one. All right, so for this one, we're going to do a table just like before. So since we're going from 2 to 10 with 4 subintervals, we need to pick our x values carefully. So we can go 2, 4, 6, 8, and 10. That'll give us 4 subintervals. Now let's calculate the y values at each of those. Again, we're just squaring stuff for this function. So we've got a 4, 16, 36, 64, and 100. Okay, so which of these are we going to be using for RRAM? With RRAM, we're taking the right endpoint's y value for each rectangle's height. So we've got a rectangle that goes from 2 to 4, the x value is 2 to 4, and it has potential heights of 4 or 6. These rectangles, since this is RRAM, they're going to be drawn to the right side here. So we have a height of 16 for this first rectangle. So when we approximate this from 2 to 10, we're going to be doing a base of 2 times a height of 16. Next, for this next rectangle between 4 and 6, we're using the height of 36 because that is the right endpoint of the rectangle. So this is going to be base of 2 times a height of 36. And then we've got a base of 2 times a height of 64. And a base of 2 times a height of 100. And then adding all this stuff up, that's going to be, let's see here, 32 plus 72 is 104 plus 128. That's 232 plus 200. That's going to be 432. On this next one, we're now going to find the area under x squared on the same interval from 2 to 10 using MRAM with 4 subintervals. So we'll bring it together and actually come up with the table together on this one. So for MRAM, we have to use the y value of the midpoint for the height. That means we need to take midpoint values that we're putting in our table. So since I've got 4 subintervals, I'm going to have 4 midpoints, so I have a table with room for 4 values. The first midpoint is going to be on the interval from 2 to 4. So that midpoint is going to be 3 for the x value. And then the next midpoint on the interval from 4 to 6 is going to be 5, and then 7, and then 9. So these are all midpoint x values, so we can get the midpoint y value. Now the nice thing about MRAM is that you don't have to choose one side or the other. There's only one y value for each of your rectangles that you could possibly pick. So pause the video and finish this one off. All right, so we've got 9, 25, 49, and 81. And when we approximate the integral of f from 2 to 10, now we're going to have a base of 2 still, because this is really the rectangle from 2 to 4, but we're multiplying that by 9 now, the midpoint y value. Then we've got base of 2 times 25, 2 times 49, and 2 times 81. And this one's a little bit gnarlier to try without a calculator, but I'm going to do it anyway. I'm going to use a little shortcut here, and I'm going to add all of the numbers that 2 is being multiplied by, and then just multiply by 2 at the end. And let's see here. I'm going to add them in a different order. So we've got 9 and 81, that's 90. And then that's going to be, let's see, 115 plus 49, that's going to be 164. So that means 2 times 164, which comes out to 328. Boom. We're going to do one more example. This one we're taking the integral from 0 to 11, and we're actually giving you the table and asking for an RRAM approximation. Pause the video and give it a shot. All right, so on this one, note that the subintervals won't always be the same size, especially when they're giving you a table. So going through here and approximating this, our first rectangle, we're going to have a base of 2 from 0 to 2 times, well, this is RRAM, so we have to go with 6 for our height. Next, we've got an interval from 2 to 5, so that's a base of 3 times the height 4. Next, we have a base of 1 times the height -1. And yeah, we can have negative heights. Next, we've got a base of 5, that's a big rectangle, with a height of -8. Multiplying this out now, we've got 12 plus 12, so 24, minus 1 is 23, minus 40, that's going to be -17. For the wrap-up on this one, we're going to do a little GeoGebra experiment. So here's a website that you can go to. Pause the video and do that. Now, questions to ask yourself while you're at this website is, what do you notice about the RAM values as you're increasing the number of rectangles, and which RAM comes closest to smaller values? So here's the website. You can change the functions, but let's use this function. I'll tell you right off the bat, I know the true value of the integral. It's going to be 42 2/3, and how I got that we'll find out in future lessons. Which RAM comes the closest? All right, let's see if we came up to the same conclusions. So here's RRAM, here's MRAM. The magic number again for this particular situation, 42 2/3. MRAM is definitely the closest out of all of those at smaller values. Let's see what happens as we increase the number of rectangles. So moving it a little bit more, what's happening to those numbers? It looks like they're all kind of converging toward the same direction. The most we can go up to is 50 rectangles on this particular app, but you'll notice that LRAM, MRAM, and RRAM, they're all very close to the same value. MRAM, again, is going to give us the best results, but in the long run, all the RAMs are converging to the same answer. In fact, if we were able to go more than 50 rectangles, say infinite number of rectangles, well, then you're all getting the same answer. But again, in the short run, MRAM is going to give you the best results. So that's it for this one. Until next time, this is Mr. Sutton signing off.